This is my second video about modeling the 3x+1 problem, the Collatz conjecture, as a Turing machine and also as a deterministic finite state machine. And I covered a lot of ground in the first video, but I realized that for somebody who hasn't thought about the Collatz conjecture in any other way than as sequences that have unpredictable stopping times, everything I'm saying may be completely foreign and hard to understand. Unfortunately, if I attempt to explain every part of the mental process I went through in the last 4 years to get to this point, it would be exceedingly boring. So I'm just going to repeat one slide from the previous video, and it's an input-output table, and it's showing the input numbers under 3 letters which correspond with congruences, very simple congruences, and I won't restate what they are here, but you might see how this works if we pick a number like 31 as the input and we see 47 as the output. And then we look at 47 as the input and we see 71 as the output, and then it's off this table. But you might notice that those numbers are familiar from the sequence for 27. And actually we could have started with 27, which would have been better. 27 input, 41 output, 41 input, 31 output, 31 input, 47 output. I think then we've caught up with the other sequence I started. And so you see how this table represents a Collatz sequence, not just one Collatz sequence, but innumerable Collatz sequences. If we extend the table infinitely, it will be the calculator for every Collatz sequence that you can imagine up to infinity. So there's no difference essentially with this table and with sequences. And one thing you might notice, and I just said it before, is that this is a finite state machine, and this little table, which I just took from Wikipedia, shows just coincidentally 3 states, A, B, and C, which correspond perfectly with the A, B, and C in this table. They're, in my case, congruence classes. In this case, they're undefined. And there are 3 kinds of input, whereas I have an infinite number of inputs. And and then between, it doesn't show the outputs, but between the input and the output, you have a transition state here, which they've just kind of not included in this very simplified table. But let's imagine the ellipsis in each cell is a transition state, and there's an output state. It's a pretty simple notion. There's a little bit more to it, but you've got the idea. And the reason this might be better than, well, not better, but a little bit more elaborate than the Turing machine is in the Turing machine, you just have one, essentially a sequence of numbers on the tape, and the head is reading the numbers one at a time. So it's a little bit different. It's obviously even the Turing machine is more hypothetical than the finite state machine. But when we say machine, we're actually not talking about machines. Well, they're abstract. and that's why they work for the Collatz conjecture. So with respect to the table, my table, ABC, you will notice, well, it's too late to notice, and for some reason PowerPoint won't let me go back, but you have their disjoint. You have three sets, A, B, and C, and their disjoint in the input side of the table. So none of the numbers in A repeat under the B column or under the C column. So that little circle with a slash through it indicates that they're disjoint. But on the output side, you can see that there's a union between A and C or B and C. There's no union between A and B. Wish I could show you the table again, but as I say, PowerPoint doesn't let you do that when you're recording video. But let me just say one thing about that table is that the lists under A, B, and C are just a series of numbers and with the same gaps between the numbers. So it's, it's just a list with three series of numbers, and the output is where it gets rather more interesting because A, B, and C each have associated with them a different operation, and maybe we'll recap that in a slide coming up. So I'm going to make some statements. I only envisage covering statement 1 in this presentation, and hopefully I can do the rest in the third presentation. But statement 1 is every odd number output has two odd number inputs. And one input number is congruent C and one is congruence A or B. So actually what I'm talking about here is merging, how sequences merge. And they merge because if you watched the first video, you would have seen that C, this class C or set C, has every odd natural number. So whereas A or B have subsets of those natural numbers. And you will find that C and A can merge, or C and B can merge, but A and B cannot. So a merge is the input of two integers that produce the same output. One input is always congruent C, the other element is either A or B, and there can only be one output. So this double input, single output property is how sequences merge. And there is such a merge for every number and even one. And so we'll show that. I'll try to show you as quickly as possible how merges occur and how the operations produce these merges. So A, B, and C obviously are operations that correspond with the congruences A, B, and C. And let's just look at 9 to 7 and 29 to 7. And so operation B is n minus 1 times 3/4 plus 1. So n minus 1 is 8 times 0.75 is 6 plus 1 is 7. And 29, which is operation C, is 28 divided by 4, which gives us 7 or so. So two sequences come together just like that. You don't see the operation C, n minus 1 divided by 4, as clearly in the even odd sequences. In fact, you don't see it at all. And that is an artifact of dividing by 2 more than twice. And I've got a couple of graphs I'll show you in a couple of slides. That's probably all you need to know about that. Did I illustrate A? Yeah, that reminded me. So in the case of A, we have this operation which is +1. So for example, 4 times 1.5, which is 6, minus 1 is 5. And again, we have this operation C acting on 21. In every case we do. But I just obviously draw your attention to the fact that 3 and 21 are multiples of 3. And you won't see those in 3x plus 1 because the multiplier is 3 in 3x plus 1. So I'm not using the 3x plus 1 function. I am using my own function, and I'll demonstrate that in a slide coming up as well. So let's go. So here I'm just showing how this merging process works for every single integer. These are bigger numbers, and that is a real sequence: 703 to 1055 to 1583 to 2375. It's growing, by the way. That's, one of those little peaks you're going to see, like a mountain, because there are consecutive operation A's, which is the only growth function. But in each case, you've got a merging operation C. And just to remind you, I think I said that every single odd integer is a result of operation C. So that would explain why every single integer, no matter how big, has a merging operation C. I wanted to quickly compare even-odd sequences with odd-only sequences. I've got 15 here, and I've also graphed it, and as you can see, the even-odd graphs are much more fun than the odd-only graphs. That's not always the case. It's just this is a pretty short sequence, and you will be maybe surprised to realize that exactly the odd numbers in the same order are present in both the even-odd and the odd sequences, and those numbers that are the same are 23, 35, 53, 5, and 1. Those are the only odd numbers in the even-odd sequence. In the odd-only sequence, we have two additional numbers, 13 and 3. 3 is obviously a multiple, or evenly divisible by 3. And 13 times 4 plus 1 is 53, which is operation C inverted there. And that disqualifies it from an even-odd sequence. The other thing was, if you put a number before 15, 4n plus 1, you got 61, and you run that sequence, you will find, surprise, surprise, that it's identical to the sequence for 15, but it doesn't include 15. So this is the artifact of the 3x plus 1 function, which is essentially, I wouldn't say defective, but it's actually hidden a lot of important information. So you can see that 15 and 61 merge on 46, and then henceforth they are identical, of course. The moment numbers, you have the same number in two sequences, it is the same sequence. That's all there is to it. Now I just want to show you that when you do this with the odd sequence, you are doing nothing more than adding that number. So you're adding one step. So in other words, you're saying that 61 is one step more than the number that's minus 1 divisible by 4, which is 15. So that makes sense. One operation, one step. And then it turns out, of course, that this is true for the even odd as well if you exclude the even numbers. So this is very significant. You've got an operation, and once you've performed the operation, you are one step closer to 1. You are always one step closer to 1 after performing an operation. So that's a little preview, peek preview of what's coming up in a subsequent presentation. Okay, I've got to show you how my function, or my superset function, works in relationship to the 3x+1 function. So in the top left I have the superset function, and you know what the operations are. We've showed those in this presentation. I think in the previous presentation we have explained the congruence classes, but maybe not in this one. But again, it's just A, B, C. So operation A is equivalent to 3m plus 1 divided by 2 in the conventional function. And I'm designating my function as 4m plus or minus 1, just as a shorthand to distinguish it from 3n or 3x plus 1. And so the 3m plus 1 function, an example would be 33 plus 1, which is 34, divided by 2, which is 17. My 1 is 11 plus 1 is 12, times 1.5 is 16, minus 1 is 17. So we have this intermediate even number in the even-odd function. I won't bother to repeat the details for B, except notice that there's a recursive division by 2. It's divided twice. And in operation C, it's the division by 2 is 3 or more times. And the difference with operation C is that the even sequence, much the same as in the previous slide, the even sequence misses out an odd number. It just goes straight through, ignoring, because of the even numbers, a division 3 times. Whereas my 1, and it goes to exactly the same end point, 11, it just adds this extra number. But it never misses a number. That's what I'm trying to say. It never skips a number from the even-odd sequence. It only adds a superset number to deal with situations like this. And I won't get into further detail, but it is a true proper superset, of the Collatz function and the sequences it produces. So I'm just going to summarize the basis case, and this is the initial case for proof by induction. And so if n equals 1, 4n plus 1 equals 5. So that gives you the shortest sequence, one step greater than 1. 4n plus 1 equals 5. And I think I mentioned just before that 4n plus 1 is the inverse of operation C. So we normally look at it in the direct function rather than the inverse function. So this shortest of sequences illustrates the universal properties of all sequences. As previously shown, the base case also demonstrates the property of merging, where we have 1 to 1 and 5 to 1. And then if we go back from there, consider that if n is any odd number, 4n plus 1 must have one more step in a sequence. And like I said, this is very key to an inductive proof, so that 5 times 4 plus 1 equals 21, which has 2 steps. And then I just go mention, why 21 as a superset number is a valid number for consideration here, because when you reverse it and start with 21, you get the same result. And that is the end of part 2. And now I'm looking at possibly needing a part 3 and a part 4 to get through this, because there are 4 other statements we need to explain, plus a conclusion. So I hope you'll stick with it and watch part 3. Thank you.